So this problem 24, and we can read it, but one thing it deals with a cylindrical tank, but the cylindrical tank is horizontal, like a gas tank underground might be. Of course, this one might not be a gas tank underground, but some of them are. So it's like this horizontal tank. Now, a horizontal cylinder. And so if you were to grab a slice of water, except this is not water, I think it's diesel fuel, so we'll do red. Diesel fuel is red. Water's blue. And when you mix them, it's really nice to drink. So if I get a slice of this, look at this slice. And even though this is a very circular, cylindrical thing, I think a slice would be, what is this shape I'm trying to draw here? I think it's a rectangle. Don't you think? If you took a slice of this, it would be a rectangular shape whose length may not vary, but whose width probably varies depending on where you are at the end of this tank, right? You with me there? See the width of this rectangle? I mean, if you're way up top, that's a thin width. If you're way down here, it's a thin width. So I think the width is changing. I think the length might be the same. Let's read the details of the problem here. In number 24, it's the top of a cylindrical gasoline storage tank at a service station is 4 feet below ground level. The axis of the tank is horizontal, and its diameter and length are 5 feet and 12 feet respectively. Okay. So it's got a length of 12 feet, a diameter of 5 feet. You got to watch those words. If it's a diameter of 5 feet, the radius is 2.5 feet. Okay. All right. All right. I'm just writing down a few little details. It says it's 4 feet below the ground. Yeah. Let me write that little detail. This is 4 feet below what I'm calling the ground, right, you guys? Find the work done in pumping the entire contents of the full tank to a height of 3 feet above ground level. Okay, so I'm pumping this stuff. Again, I grab my slice of gasoline. This is actually gasoline. And I pump it up 3 feet above ground level, I guess, is what they just said. Now look, this is what I would call a rough picture. What I really need is I need this picture on an X and a Y axis. And I could lay my X and Y axis on here, but the truth is I'd like to just start over with a better picture. This is my rough picture. Here comes my better picture. I need an X and a Y axis. And again, you may be tempted to say, okay, that X axis is ground level. You know, that does seem to make sense, but I beg to differ. For the advantages of this problem, I think what I should do is I've got this circuit, I'm trying to, again, what's funny about these is I'm taking a three-dimensional tank and I'm putting it on a 2D picture. That's a little funny. But what I'm looking at is a side view of this, and it's actually, I want a front view of this. And it looks to be circular. And if it's circular, where would you put your circle if it was up to you? I would center my circle on the origin, of course. I mean, maybe not of course, but you learn that that's smart, to center your circle at the origin. So I'm going to put the circular end of this tank here, and then it kind of goes into the board. You know, here I mean, this is, I hate to clutter up my picture. But this tank is kind of heads into the board, 12 feet into the board. Are you with me? I'm looking at this circular end, and it's going 12 feet into the board there. So now, wait a minute. Let's, again, that does clutter up my picture. I hate that. What's the radius? 2.5? 2.5. Now, wait a minute. If this is 2.5, right? Where is the, let's see, where's the ground? What's the ground? What's the ground?
That's 6.5.
Okay, the ground is 6.5 because it says it's 4 feet up. See, back to my rough sketch. I would label the ground 6.5, but where am I pumping it to? I'm pumping it 3 feet above the ground. So I guess I'm going to 9.5. You guys with me? I decided to center my circle at the origin. It's radius 2.5. From there, I go up 4 feet to ground level, and then I go 3 feet above that because that's what the problem wanted.
Okay.
If you remember, to find work on these problems, here's what we needed. We needed an integral. We needed the weight of the substance. With water, it was always 62.4. With this gasoline, it's 42. So we needed that weight. I'll fill that in a minute. We also needed, if you remember, the area of a slice of water, but in this case it's gasoline. And we also needed the distance that we're pumping this gasoline or water. That was the game. That was the game. I kind of wrote that down for you. That's a good formula from the other day. By the way, yeah, okay. All right. So here we go. Let's see. So I need an arbitrary slice. I mean, that's a decent picture, but if I move it over to this picture, my arbitrary slice sort of looks like this. It does go back into the board there. 12 feet, is that what we said? Yeah, this is a rectangle. It's funny. I know it's a cylindrical tank, but when you put it horizontal, a slice is a rectangle. Now, here we go. We're getting there. We need the area of the slice. We need the distance we move the slice. The distance is always pretty darn easy. Here I go. Remember, I'm grabbing this slice and I'm moving it all the way up here to this point. What do you call that distance? 9.5 minus y. That's what you call that distance. We practiced it a little last week. It's right. I mean, from the x-axis up, we call that distance y. So that's 9.5. So what I've drawn there is 9.5 minus y. Right. If you don't mind, I'm just going to put that right here. 9.5 minus y. That's the distance. The weight of the water was 42. I mean, gasoline was 42. Okay, here we go. I need the area of this slice. I'm going to get rid of that little y. I need the area of this slice. Well, it is a rectangle. I think the area would be its width times its length. I think its length is a solid 12. What about its width? It changes, so it's going to be a variable. Well, we'll get there. I meant, I wanted to start. Well, yes, I wanted to start kind of basic. What would you call that width? Well, no, it ain't really a diameter if it's here or here. I mean, all right, I'm sorry. What would you call that distance? X. Okay, now what I just labeled x is not the width. What would you call the entire width? 2x.
2x.
Brilliant. That's the key. That width is 2x. Do you see it? Mm-hmm. I mean, from the y-axis over, we call that x. That's half the width. The width is 2x. So the area is 2x times 12. I mean, but what is x? Oh, I need x in terms of y, so I need the equation of the side of this tank. You know, we did that. We had a line the other day. We had a circle the other day. This is the equation for the side of this tank is a circle of radius 2.5. What is the equation of a circle of radius 2.5? It's x squared plus y squared plus, equals.
Equals 6.25 is 2.
Right, equals 2.5 squared. 2.5 squared, she says, is 6.25, right? Okay, now I want x. So what's x? The square root of
6.25 minus.
I need x. The equation of the circle is this. I need it solved for x in terms of y. Here I go. This is my x. So my area becomes, if if you don't mind, can I call that 24 times this x, which is the square root of 6.25 minus y squared. We're awesome. We are awesome. You are awesome.
Picture says everything.
Any questions? There is one last little detail here. I need the bounds. This slice of gasoline to pump it all out of this tank and move it all up there like we're trying to do. Where this gasoline moves from?
-4? No.
The gasoline moves throughout this region where it lives. So the gasoline moves from negative 2.5 to 2.5.
Oh.
That's where you integrate from. You're taking the distance into account with your distance. You're moving this, you're grabbing these slices of gasoline that live from negative 2.5 to 2.5. That's where you integrate from. That's a good problem.
Yeah.
I mean, we did similar things, but we didn't do this shape. We didn't do a horizontal cylinder the other day. But there's a horizontal cylinder, which results in a rectangular slice of gasoline. Yes.
Could we use symmetry for this problem?
You know, that's a little dangerous. When we do these pumping water problems, and using symmetry is a little dangerous. I mean, I used symmetry sort of when I said that distance was x, so the whole width was 2x. I use that symmetry. But, you know, what you can't do in these problems, it's interesting. I can't say that emptying the top half is the same as emptying the bottom half. Why not? It's the same amount of gasoline, and that in the top half of this tank is the same amount of gasoline as the bottom half of this tank, but
There's more distance to travel, so more
it
pressure.
takes more work to do the bottom half because it travels more distance.
Right.
Good. Yeah, work is funny like that. Right, I can't. Exactly. You know, it kind of reminds me of the springs. You know, if you did the work for compressing a spring 2 inches, that'd be a certain amount of work. What if you did 2 more inches? It's not the same work, is it? Once it's already, I mean, let's say you did the work from 0 to 4. That's some amount of work. Is 0 to 2 half of that? No. It's less work than the first 2 inches are less work than the next 2 inches, right? Right. So the work's kind of...
Accumulation.
Okay, good. Any other good questions?
I have a question.
Okay.
My question is, when do you just put y on these problems? I'm not talking about this one in general. And when do you take like where you're going minus y?
Well,
sometimes it works for both. I'm trying to figure out. That's the only thing I can't.
When I draw distances from the x-axis up, I call those y. When I draw distances from someplace up to 10 or something like that, that's 10 minus y. So it's that. So there was one problem last week where we were pumping the water through a hole in the bottom of so the water was moving this way. Anyway, a distance drawn from the x-axis up we call y. A distance from some place to 10 is called 10 minus y. I mean,
so that would determine what would go in there, depending where you're pumping from.
Or where I'm pumping to or from, right? It's the distance I draw from my slice